All right, class, welcome to this midterm review. So we're going to review all the concepts and all the topics from 1 and 2 that are given in this table below. So these are the same exercises that you have in the review that was passed out. So let's look at the first one. So we have certain students took an exam for a maximum of 50 points. The data is given below. So we want to determine, is the score on the exam a categorical or a quantitative variable? So the score on the exam is a number that makes sense to be averaged. If it's a number that makes sense to be averaged, then in that case it will be referred to as a quantitative variable. If it's like a label of some sort that it doesn't make sense to do the average of, then that would be referred to as categorical. Eye color, hair color, characteristics, basically. Construct a dot plot of the results. Okay, so let's start with the dot plot then. So looking at our numbers, we're gonna be using our numbers to construct this dot plot. We're gonna do a single number line, and since our numbers vary from 2 through, let's look at all the numbers here. It varies from 2 through 50. Let's go ahead and let's go by twos here. Starting at 2. You can go by whatever scale you choose. In this case, I just wanted to go by twos, but whichever one you choose, you can go by threes, you can go by fives. Okay, so there's my number line, and all I'm going to do is I'm going to stack dots for every instance of that number. So I have a 1, 2. I have 1, 4, 1, 8, 1, 10, 1, 12, another 12. I got a 15 between 14 and 16, 20, 23, 25. I got another 23. I have 3 28s. I have 2 29s. 1 33. 1 35. 1 36. 1 42. Another 42. 44. And a 46. Kind of looking at the distribution here, it kind of looks symmetric. You can kind of tell, you have a bunch of ones here, maybe a 2, but then you have a peak here in the middle, and then you have sort of leveling out here with a little bump here. So it kind of looks roughly symmetric, but there's our dot plot. Now the next thing that they want is a stem plot. Okay, so to do the stem plot, we'll need the stem on one column. We'll need the leaf on the other column. And we can use the dot plot here for our stem plot. So because we have all the data up here, so we can use it for the stem. So the stem, so basically the stem is the leaf is like the ones digit. Okay, so the leaf is the first digit in that number, and then the stem is the rest of that number. So if I have the number 2, right, well, this is where we do our key. Okay, so we need a key here. Let's do it off to the side. So if for our key, if we have the number, let's say 28, well, the number 28 is 2. Okay, so if I have the number 28, then that would be 2 and 8. So 8 will be the leaf, 2 will be the stem. So that's how our key is going to work, okay? And if we have like the number 2, then 0 is the stem and 2 is the leaf. So for our stems, we have 0, we have 1s, we have 2s, we have 3s, we have 4s. Do we have any 50s? I forgot. There's a couple of 50s here. We have a 46. We have a couple of 50s. So 1 and 2. I forgot about those 50s there. So make sure to include that in the dot plot. So we have a 5 as well. Okay, so let's go to the stems of 0, which would be the number 2. We have the number 4 up here in our dot plot. I'm just looking at the dot plot up here. And then we have the number 8. And then that's it for our leaves. For the number 1, we have a 0 for the leaf. We have 2 12s, so that will count as 2 2s. We have a 15, and that's it for our stem of 1. And let me do this like this so we can kind of tell the difference. For 20, we have 0 for 20. We have 2 23s, so 2 3s. We have a 25, and we have 3 28s, and we have 2 29s. For 30, for the 30s, we have 33, we have 35, 36, and that's it. For 40s, we have 2 42s, we have a 44, and a 46. Okay, and then for 50s, we have 2 50s. So we can kind of tell, it looks roughly, symmetric, kind of, just looking at this distribution. Roughly, most of the numbers are around the 20s, right? So, and with very little 50s, very little a few zeros. So it's probably going to be roughly symmetric, but we'll do our histogram as well. So part C part D wants us to do a frequency table for these results. Okay, so we're going to do a frequency table. All right, so for the frequency table, let's see here. We're going to calculate our class width. So we need to calculate this first. So our class width is equal to our range, so our maximum minus minimum, divided by the number of classes. So our maximum here is, in this case, it's 50. That's the biggest number, right? Our biggest number is 50. And our smallest number was 2, divided by the number of classes. You get to choose this. And here in this problem, it says to choose 5 classes. So it says choose 5 classes. In that case, you're going to divide by 5 here. Okay? Usually it's, between 5 and 20 classes is a good rule of thumb, around there. You don't want too many and you don't want too few. So in this case, we have 48 over 5, which is going to be 9.6, I believe. Yeah, it's going to be, let's see here, 5.4. So 5 goes into 48 about 9 times. So this will be 9.6. All right, and then we're always going to round this up. So we're going to round it up to 10. So always round up. Now that we have that, we can set up our table. So we have our interval on one side, and we have our frequency on the other. So our interval, we start with our smallest number, which is 2. So we want to go from 2 to less than, and then this is where you add your class width. So 2 plus 10, right? It's going to be 12, so that goes here. All right, and then the next one's going to be 12 plus 10, which is 22. So it's going to be from 12 to less than 22. So this is where you add your class width. Next one's 22 to less than 32, 32 to less than 42, and 42 to less than 52. And you stop until you get to 5 classes. So in here I have 5 classes, 1, 2, 3, 4, 5. Why 5 classes? Well, because that's what we chose. We chose 5 classes. If you chose 6 classes, then you would continue and to do 6 classes. Now, if you got a whole number here, let's say you got a whole number from this calculation. Let's say you got exactly 10. If you got exactly 10, like a whole number, then that means that you're going to go 1 extra class. Okay, so instead of doing 5 classes, you'll go 6 classes. And that's because if you get a whole number, you won't be able to round it up, right? So if you're not able to round it up because it's a whole number, then in that case, just go an extra class. All right. Also, keep in mind that if you had 9.2 here, you would still bump it up to 10. Okay, so you would still round it up to 10. So just some rules that you can keep in mind. All right, now, so for frequency, we need the numbers that belong from 2 to basically 11 here, less than 12. Okay, so from 2 to less than 12. In that case, we can kind of tell from here. We have 1, 2, 3, and 4. Because we got a 2, we got a 4, we got an 8, and we got a 10. So there's 4 numbers that belong in that category. From 12 to 22, from 12 to less than 22. So we got 1, 2, 3, 4, 5, or wait, 1, 2, 3, 4, because that would be 20. So we got a 12, 12, 15, and a 20. So that's also 4. From 22 to 32. So from 22 to 31, basically. So we got 23, 23, 1, 2, 3, 4, 5, 6, 7, 8. 8 numbers, because then when the next number is 33. So we have 8 numbers. So from 30, so from 32 to 41, basically. So 1, 2, 3. So about 3 numbers. And then from 42 to 52. 1, 2, 3, 4, 5, 6. So we got 6 numbers. All right, so this is looking kind of roughly symmetric. Just kind of looking at that peak, 4, 4, 3, 6. It seems kind of symmetric. Or roughly so. So now that's our frequency table. That's done. Next, we're going to look at our histogram. So let's do that over here. So for our histogram, we need our frequency on the y-axis. We need our interval on the x-axis. So we have 2, 12. So when we do this, we form sort of like an L. Okay, we use this to get our numbers. So 2, 12, 22, 32, 42, and 52. So 2, 12, 22, 32, 42, 52. And these are called our classes, by the way. So our interval or classes. Okay, so for frequency, we're going to go by twos here. Or actually, we can go to 8. 1, 2, 3, 4, 5, 6, 7, 8. So it's 8, 7, and so on. And so now when we do our rectangles for our histogram, we're going to go from 2 to 12. It's a height of 4. Okay. From 12 to 22, it's a height of 4 again, and the bars have to touch. From 22 to 32, it's a height of 8. 32 to 42 is a height of 3. And then this is going to be a height of 6. Okay, so we'll say this is kind of roughly symmetric. It's a little bit off, but it's roughly symmetric just by looking at this. So the shape is roughly symmetric. Or I will say I say roughly, but it should be you should say approximately. Approximately We won't say symmetric, we'll say it's about bell-shaped. Okay, so approximately normal or bell-shaped. Okay, so approximately normal or bell-shaped. Now, because it is approximately normal, this means, so from part F is asking the shape. Part G is asking which value should be reported as the measure of center. So for part G, which value for measure of center / variability. So that's what it was asking. So if it's approximately bell-shaped, you're going to use the mean as the measure of center. And that's because if it's normal, you can rely on the mean to find the middle. Now, if it's not approximately normal, then you're going to be using the median. Okay, the median is not influenced by outliers, and so it can be used for things that are not bell-shaped. All right, so that are not, that are like skewed, for example. And then in this case, for variability, you're going to use, if it's approximately normal, you're going to use the standard deviation as the measure of spread spread or variability. If it was skewed, you would be using the interquartile range, okay, for that. So just going over that, that concept. All right, so next thing we want to do is find the 5-number summary. So the 5-number summary is our next stop here. The 5-number summary includes our minimum, first quartile, median or second quartile, third quartile, and maximum. Okay, so in this case, our minimum is easy. It's going to be our smallest number, which is, 2. Our maximum is our biggest number, which in this case was 50. That was our biggest number. Now for our quartiles, we'll need to sort the numbers in order. Okay, so we'll have to sort our numbers. So if we sort our numbers, we have 2, 4, 8 from smallest to largest. Okay, so that's our data sorted. So now that we got our data sorted, we can find the median, so the middle number. So we're gonna work our way towards the middle here. So we have, let's see, we have 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2. So there's our median. So our median is going to be our second quartile, which is 28. Our first quartile. So since our median is 28, that means that that's our middle number. So that means that we're going to be finding the median of this left half, and then finding the median of this right half. Okay, so we have here 1, 2, 1, 2, 1, 2, 1, 2, 1, and 2. So we have two middle numbers, so that means we have to add them up, divide by 2. So in that case, that's what, 27 over 2. Let me double check. Yeah, okay, so in that case, 27 divided by 2 is 2 goes into 27 13 times, so 13.5. All right, now for third quartile, let's see here. We got 1, 2, 1, 2, 1, 2, 1, 2, 1, 2. So we got those two middle numbers. So add them up, divide by 2. So in that case, that's 78 over 2, which is 39. All right, so there's our 5-number summary. Next up, they want us to find the interquartile range. So the interquartile range, you basically subtract the third and the first quartiles. So it's 39 minus 13.5, which is 20, let's see here, should be 25.5 for our interquartile range. All right, and that sounds about right. So now the next thing is they want us to construct a box plot. So let's do our box plot. So this is where we use our 5-number summary. So we're going to do a number line. So from 2 to 50. Now for our box plot, technically we have to calculate our outliers, right? Because we want to do a modified box plot. Okay, so we want to do a box plot with outliers. So before we even touch the box plot, we need to do our outliers. So let's do our outliers off to the side here. So outliers, we need to see if we have any outliers. So we need to calculate our lower bound or lower fence. Sometimes I call it lower fence, lower bound, same thing. And then our upper bound for outliers. Okay, the lower bound, if you recall, this is the 1.5 IQR rule. So this is the first quartile, take away 1.5 IQR. And then the upper bound is the third quartile, add 1.5 IQR. So our first quartile, we said was 13.5, so 13.5 minus 1.5 times our IQR was 25.5. All right, so we'll have to do that real quick. All right, we got 24 point, or we should get negative 24.75. And then here we have third quartile, which is 39 plus 1.5 times 25.5. So we'll calculate that real quick. All right, we get about 77.25. All right. So in this case, our outliers are if there's any numbers between those, or if there's any numbers less than this or greater than this, then they're considered outliers. So are there any numbers that are outside of those values? And the answer to that will be no, right? 50 is the biggest number, and 50 is not greater than 77. So we're good, and there's no negative numbers. So no outliers. So we don't have to worry about doing outliers in this case. If we did have to do outliers, then when we do the box plot, right, you would have to include, we're going to still include our upper and lower fence. This is our upper boundary and our lower boundary. Then you would have, an outlier there. If there was an outlier, you would indicate it with an X, okay? But here we're not, we don't have any outliers. Okay, so now that we know our outliers, we're going to label our fences and our number line. So let's start with, we're going to go from 2 through 50, probably the same way that we did. Let's actually go by, let's start at 0 and we'll go to, since our fence is about negative 25, well, we'll start at, we'll do, this is negative 25, and we'll go by, yeah, let's go by tens. It's up to you what you want to go by, but I feel this is, we'll make our number line shorter. Okay. So our lower fence is about negative 25. Our upper fence is about 77, so we'll need to go a little higher here. Okay, so about 77, so around here. And then our minimum, which is 2, goes around, this is going to be 0 between those two, so 2 will be around here, so we'll indicate that with a vertical bar. Our first quartile is 13.5, so it's around here. Our median is 28, so around here. Third quartile is 39, so it's going to be around here. And then the maximum of 50 is going to be in the middle between those two numbers. And then we draw our box for this part, and we draw our whiskers. And there's our box plot. All right, so that's how you draw a box plot. Looks like this is roughly symmetric. Looking at the whiskers, right? The whiskers are about the same length. This median is about the middle. It's approximately in the middle of the box, so looks like it's roughly symmetric as well. So it looks like all of our graphs agree that it's roughly symmetric. In that case, that is our box plot. The next thing we're going to move on to is the 45th percentile. We want to do percentile. So they're asking for what is the 45th percentile? So the percentile formula we're going to be using, or the formula we're going to be using, is we need the location of that percentile. So the location is n plus 1 times percentile out of 100, which in this case is, we have, 25 numbers? So 25 plus 1 times 45 out of 100. And if you did that, you get 20, your location is 11.7. Now, if this were a whole number, like 12, then this means that your 45th percentile is the 12th number in your ordered list. Okay, so that's this list right here, your 12th number. And in that case, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, it will be 28 for your number. Now, since we are looking at 11.7, this means we're interested in those two numbers there, okay? The 11th number and the 12th number. So our number is sort of between the 11th and the 12th numbers. So that means our 11th is 25, our 12th is 28. So we're going to write those two numbers out, because we're going to need to calculate it in the value. So the value of the 45th percentile. So the value formula, the formula in general is, you take your previous, you take the what I call the future value, or the forward value, minus the previous value, times your decimal part, and that's this decimal part of this. The decimal part of this is 0.7, and then plus your previous value. Okay, so that's just a basic formula that I use to find that. So in order to calculate that, this is your 12th number, and then this is your 11th number, because this number is between 12 and 11. And your 12th number, we said was, what was that 12th number? It was 28, right? 28. And then our 11th number is 25. So we have 28 minus 25. And then our decimal part is 0.7 right here, plus our previous value, which was 25. Now if you do that, you get 27.1 for your decimal, for your 45th percentile. All right, so that's the 45th percentile. The next thing that they want is, let's see, so now they said Tessa's score was a 25. What was her percentile? So basically they're saying Tessa's score was a 25. 25 is what percentile? Is what they're asking. So this one's actually easier. So to actually calculate the percentile, we find the number of values less than a given value x over the total number of values times 100. So in this case, x is 25. We're interested in the number of values less than 25. So the number of values less than 25 out of, and we got 25 numbers times 100. So how many values are less than 25? Well, in this case, if we look at it, there are, let's look at our list here. Number of values less than 25. So that would be all of these. That would be all of these guys, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it looks like 10 numbers less than 25. So we have 10 out of 25 times 100, which is looks like the 40th percentile. Let me double check that number. Yeah, so 40th percentile. There you go. That's our guy. All right. Next up, let's go back to our previous page. Okay, so looks like we did all the things. We did the frequency table, stem plot, histogram, box plot, all that stuff. Number 2 is the exact same setup, just different numbers. So I'm not going to do that again. Just the same process for number 2. Just extra practice for you. Number 3, determine whether the variable is categorical or quantitative. So age. Age is numerical. It makes sense to do the average of a set of values for age. So that would be quantitative. Marital status, that would be something that is, a label. It doesn't make sense to do the average. So that would be categorical. Earned income, you can take the average of you could take an average income, and that would make sense. So quantitative. All right. What is the meaning of the standard deviation? What does it measure? So this is more of a conceptual question. Let's talk about the standard deviation. So this is problem number 4. So remember, the standard deviation is what we call a measure of variability. Okay, measure of variability measures the spread. So the standard deviation is a measure of variability. So measures, and basically what it does is it measures the average spread. So the average, it measures the average, what we call deviation. The deviation is, so it measures the average deviation, or the deviation is basically how far you're away from the mean, so the distance from the mean. So that measures the average deviation or distance from the mean. Okay, so basically it basically measures how spread out the data is from the middle. Okay, that's basically what it does. So, and that's our definition. That's what it is. So I'm just going to kind of elaborate on that. So let's say this is your data. This is 2, and this is 20, and this is let's say this is 100 actually. That's pretty spread out, right? Now let's say we have a lot of numbers. Let's say our next biggest number is like 50 or something like that, and then this is our smallest. So let's say we have a lot of numbers between 2 and 50, and let's say the average is 20. Let's say our average is 35. Then the distance from 2 to 35 is, 33. The distance from, and this is actually negative 33 because negative means to the left. And then the distance from 35 to 100, right? That's huge. That's about 65. And then what we do is we average all of those distances. From 35 to 50 is about 15. So, and then we measure all, we square those distances, right? We square them, we add them, and then we do the average. And so that's like the average deviation, the average distance from the mean. So it gives you an idea of how spread out the data is, because if it's a large number, that means the data is spread out. All right, so that was number 4. Number 5, given the data 1, 5, 8, 3, 10, 2, compute the sample standard deviation. All right, so let's do that one. I'll go ahead and write out the data since it's not too large here. So we have 1, 5, 8, 3, 10, and 2. Okay, don't worry about the squiggly brackets. I just do that to kind of contain the data. So now what we want to do we want to calculate the sample standard deviation and the population standard deviation. So the symbol for the sample standard deviation, the symbol for that is S. The symbol for the population standard deviation is lowercase sigma. Remember that a population is everybody that you're studying, and then the sample is a portion of that, of the portion or subset of everyone that you're studying. Okay, so in this case we're going to calculate both. The sample standard deviation is given by this formula, so square root of the sum of the deviations from the mean squared divided by n minus 1, the number of data values minus 1. This is very similar. So remember, this is the sample mean. This is the sum of the deviations from the population mean, which we use mu, so the population average, squared over the population size. And this n right here is the sample size. Okay, different symbols, but they mean the same thing. Mu is the same thing as x bar because we're using the same data here. Okay, we're using the same numbers. All right, so mu is going to be the same thing as x bar. So x bar in this case, which is going to be the same thing as mu, right? Our x bar is, we just average out the numbers. 1 plus 5 plus 8 plus dot 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 all the way to 2 divided by, we got 6 numbers. So our x bar is, we'll say it's 4.8, 4.83. Our mu is going to be the same thing, 4.83. So now what we're going to do is we're going to set up a table. X minus x bar, and x minus x bar squared. So our x, we're going to list out all our x's here. We have 1, 5, 8, 3, 10, 2. Now we're going to subtract. We're going to do x minus x bar. So the x value minus our x bar, which is 4.83. So 1 minus 4.83. In this case, we get negative 3.83. We repeat this process doing 5 minus the x bar, and so on. We get, and I'll tell you what the numbers that we get. We get 0.17. We get 3.17 for this. Negative 1.83. 5.17 and negative 2.83 if we repeat that process. Next, we square the numbers from the second column. If we do that, we get 14.67 around. I'm just rounding. We get 0.03 for the next one, 10.05, 3.35, 26.73, and 8.01. Next, we add up this last column. So we have to add up that last column. Remember that this sigma means you add, or the total. Okay, so we're totaling that last column. If we add this up, we get 62.83. All right, next we plug that into our formula, right? So now we know what this is, so we can plug it in. So we have S equals square root of that number, 62.83, divided by, we have 6 numbers minus 1, and we do that calculation. So if we do that, we get 3.54. So 3.54. And then same thing for the sigma. Sigma is going to be still the same number, but divided by 6, our population size, instead of our sample size. We use 6 instead of 6 minus 1. And we get about 3.23 or 24. We'll round to 24. All right, those are our values. All right, next up, they want us to interpret that value. So if we want to interpret this value, they want us to interpret S. Okay, so interpret S. So this number, this 3.54 number that we have, so this means that the average or typical distance from the mean is approximately 3.54 units. If we were talking about test scores, then you would have to interpret it in terms of test scores. So you would say the typical the typical distance from the average test score is about 3.54, or the typical you would say something like that. You would say the typical distance from the average test score is 3.54, something like that. All right, so now let's look at the next question. All right, so number 6 is the same thing. Number 5 is actually, they just want the sample standard deviation. Number 6 wants the population. We kind of did both when we did number 5, so that way you know how to do both. So we won't do number 6. It's the same process. So number 7, Mrs. Causey asked her students how much time they had spent using a computer during the previous week. The following figure shows a cumulative frequency, relative frequency graph of her students' responses. So, all right, then they want the percentile. At what percentile does a student who used her computer for 7 hours last week fall? So we're looking at 7 hours, right? So this here, between 6 and 9. So this is, let's see here. So this will be, this average right here, this will be about 7.5 in between 6 and 9. So if they're asking for 7, it's, you know, around here. So if they're talking about 7, then we do a vertical line up to that point on the graph. We're interested in where that is on the graph. 7, so about 7 hours per week. Looks like it's about the 60th percentile. All right, so for part A, this is the 60th percentile. This means 60% of people used a computer less than 7 hours. Okay. Estimate the interquartile range from the graph. So the interquartile range, remember that IQR is the third quartile minus the first quartile. So, but remember, in terms of percentiles, right? The third quartile, remember, a quartile breaks the data into 4 pieces, right? Which is 25%. So which means that the first quartile is really the 25th percentile, which I'll call P25. And in the third quartile is really the 75th percentile, right? So which I'll call P75. Which means that we'll need to find the 75th percentile and the 25th percentile. So in this case, our 75th percentile, I'm going to erase this now. Our 75th percentile is here. This is 75. This is our 25th percentile. So we'll trace it on the graph. So this looks like about 2. 75. All right, so our 75th is around here. Which kind of looks like it's around the 11 mark. So it kind of looks like about 11. Depending on how you did it, it probably helps to do a straight edge, to use a straight edge for this part of the problem. But either way, it's if you said it's about 12 and then the other one's about 3, the other one's 11 is about 2, you can still subtract them, right? So 11 minus 2, and you get about 9. The interquartile range will be the same if you did 12 minus 3, if you thought it was like either one of those numbers. But it's about 9, estimate. All right, so part C, find the number of hours last week for the 72nd percentile. All right, so the 72nd percentile, this means that you want to go, let me erase all this. So if we're doing 72nd percentile, this has to be below 75, so it's probably around here. So go to the graph. It looks to be about 10. So we'll say it's about, between 9 and 12. It's about 10.5. So we'll say about 10. So it's approximately 10 hours for that week. All right. Let's look at the next problem. Number 8, if the shape of a distribution is symmetric, is the mean greater than, equal to, or less than the median? What if the shape is skewed left? It should say what if. What if the shape is skewed left or skewed right? Okay, so let's talk about that concept. So let's go down here real quick. Okay, so for number 8, I believe that was. So let's talk about symmetric. So if you have a distribution that is symmetric, or it should really say normal, not really symmetric, but that's fine. If it's normal, normal is symmetric anyways. So if it's normal, then you're going to be using the mean as the measure of center, okay? If it's skewed, you're going to be using the median. Okay, so for a normal distribution, the mean is equal to the median, and they're both in the middle, okay? For something that is skewed right, if it's skewed right, that means the curve looks like something like this, where the left tail is longer, right? The positive tail is longer, the negative tail is shorter. In this case, the median is the middle number, right? So the median will change a little bit, right? So the median is the middle, which is, probably around here or something like that, right? So we'll call that the median. And the mean is going to be skewed to the right, okay? Because let's say this was test scores. If somebody got 100 and most of the students got a, let's say most of the students got a 35% on a test, right? And the median is, say 50%, right? Then that means that if you were to do the average, well, the average is going to be on the lower end, right? The average is probably going to, or is going to be still low, but it's still going to be, greater than 35. So the average is going to be skewed a little bit because maybe you had a couple of students got 100% on the exam, right? And so they kind of messed up the test. They kind of messed up the average. So the mean is to the right. In this case, the median is going to be less than the mean. So if it's skewed right, the median is less than the mean. If it's skewed left, right? If it's skewed left, so let's talk about skewness to the left. That would look like this, right? So in this case, let's say most of the students got a 75%, and you got maybe a student that got a 0 or something on a test. Well, that just messed up the entire average, right? If the median is around here, then the average is going to be, around here. It's going to mess up the average. It's going to make it like 60% or something like that. So now this is the mean. In that case, the median is now greater than the mean. So you'll have to know like the differences between those two as far as which one's greater, which one's less than. All right, so that was number 8. Number 9, which distribution has outliers that are small? So kind of going back to this graph, this one has a small outlier. See this one right here? That's a small number and it's an outlier. So that will be a left skewed distribution. So for the problem that they're asking for, which distribution has outliers that are small, that would be a distribution that is skewed left. So a negatively skewed distribution. Negatively means left skewed. So negatively skewed distribution. Now determine whether the correlation coefficient is close to 0, 1, or -1. Is it weak or strong / moderate? Is it a positive or a negative correlation? So remember, correlation is the strength of the linear relationship between two variables. Our two variables here are hybrid hatching success and the years since divergence. Don't ask me what that was for. That's just an example. So this is a bunch of data, right? And it looks like it's going into a line, right? So it looks like the line of best fit, maybe something like that, right? So it looks like it's trending downward. So that means it's a negative correlation, right? So it's a negative correlation if it's trending downward. Now, is it strong? Well, it looks like a lot of the lines kind of go towards this blue line that I drew. It kind of looks like most of the lines are there. These guys, are far away from it, but so I would say maybe moderate, right? So moderate strength. So moderate strength. And if it's moderate / strong, that means it's going to be close to 1, okay? Or -1. So because it's negative correlation, it's going to be closer to -1, right? If it was positive correlation, it's going to be close to 1. All right, so -1 or 1 means perfect. Everything fits on a perfect line. And then 0 means it doesn't fit at all. There's no pattern at all. There's no linear trend. All right, so that's our answer right there. Number 11, looking at the two residual plots, which model is a better fit? Explain. So we have a quadratic model on top, a linear model on the bottom. They give us our residuals. Remember, our residual means error, right? So residual means it's the same thing as our error in our prediction. Okay, so we'll have a model. If we have made an error in our prediction, that's our residual. So we're looking for lack of patterns here. Is there anything that is completely random? So if you look at the linear model, it looks like most of the numbers seem to form this weird pattern, right? There seems to be a pattern in those numbers. So therefore, there's a good chance that our linear model is not good. All right, so it's not valid because there is a pattern in our residuals. Okay, so if you look at the quadratic, it seems to be kind of random. It seems to be kind of scattered, down, up, up, down, up, down. It's randomly scattered, so there doesn't seem to be a trend. So in this case, the quadratic model is a better fit because the residuals are randomly scattered about the zero line. Okay, and that's what we're looking for, lack of patterns. Okay, so lack of trends. So there's a lack of trends. All right, so that's number 11. Number 12. A survey was designed to study how business operations vary according to their size. Companies were classified as small, medium, or large. Questionnaires were sent to 200 randomly selected businesses of each size. Because not all questionnaires were returned, researchers decided to investigate the relationship between the response rate and the size of the business. The data are given in the 2A table. All right, so we have our data here. And what number is it? This is number 12. So which variable should be used as the explanatory variable? Explain. Well, it's just said in the problem. They're asking, they're trying to investigate the relationship between the response rate and the size of the business. So that means that depending on how large the business is, will determine what the response rate is, right? That's what they're trying to investigate. So that means the business size is the explanatory variable because they're trying to see if the business size, the size of the business will influence the response rate. Okay, so this means that, okay, so we'll say this is the business size. It can be used, it can possibly be used to predict response rate. All right, so that's what we're looking for part A. Now part B, construct a segmented bar chart to summarize the relationship between the business size and whether or not the business replied to the survey. So let's look at, we're gonna have to go to the next page here. All right, so we want to do a segmented bar chart. So segmented bar chart. All right, so I'm just going to do a quick chart here. So yes and no, small, medium, large. Okay, just so that we can look at the results here. So we got 125, we have 75, 81, 119, 40, and 160, and they all total to 200 here. And here the total is 246, 354, and 600. All right, so we said that our explanatory variable is going to be the size. Okay, so this is our explanatory variable. I'll just box that. So now we want to determine, okay, what is the percentage of businesses that will say yes if they're small. Okay, so we'll need to calculate that. So we'll say a small business that says yes. What is the percentage of that? Well, okay, so there's 200 small businesses, right? So If you're small, then that means it's going to be 125 out of 200, which in that case is 62.5%. If you're a small business that says no, well, that's going to be 75 out of 200, which is 37.5%. If you're a medium-sized business that says yes, well, that's 81 out of 200, and that's 40.5%. If you're a medium business that says no, then 119 out of 200, which is 59.5%. If you're a large business that says yes, then that's 40 that say yes out of 200. So that seems like 20%. Large business that says no is 160 out of 200. Looks like 80%. There does seem to be a trend in those that say yes and no. So it seems that if you're large business, you're more likely to say no than you are likely to say yes. That's what it looks like here. But we're going to draw the segmented bar chart using the results here. So here, this is going to be our percent here. So percent response rate. We're going to go all the way to 100, so I'll go by tens here. And then our variables are, a size of business here. So keep in mind that because this is our explanatory variable, this will generally go on the x-axis. So I forgot to mention that. Since that explanatory variable usually goes on the x-axis. So in this case, just make this the x-axis just so that, you're not confusing anything. I mean, technically, you could switch these and say, yes and no on the x-axis, but for all intents and purposes, let's make the explanatory variable always be the x-axis. Okay, so this is explanatory. Let's put it on the x-axis, just so that there's no confusion. So we have S, M, and small. So we have a small business, a medium-sized business, and a large-sized business. And then we'll need our key here. Okay, so for our key, we're going to say that a bar that is shaded like this, you can use colors here, but on the test you may not have that, right? So we're just going to use this. So this is going to be for a yes, and this is going to be for a no, okay? And that's going to be our key. So in this case, for small business, yes was 62.5%. So we're going to do it about the 62% mark. And that's said yes. No, you're just going to go all the way to 100%. And that's no. Medium, yeah, that's a yes was 40.5. And then the rest said no. And then large business, yes was 20%, and no was the rest. So is there an association between the two variables is probably what the next question is going to ask. Yeah, determine if there's an association between the size of business and whether or not the business replied to the survey. So, looks like the larger the business, the smaller the response rate. That's what it looks like. There seems to be an association between the response rate and the size of the business. So there seems to be an association between size of business and the response rate. as the size of the business increases, the response rate decreases. Okay, and this is based off of our results here. So that's how you use a segmented bar chart to determine if there's an association between two variables. Now, if the bars were roughly the same, like if, for example, the small was 60%, medium was 58%, large was like, I don't know, 52%, then those are pretty close to each other, right? In that case, there would be no association. All right, so if the bars are about the same, no association. All right, so let's look at the next question. It's actually the last question. So below is the data for the height of a female child over time. So make a scatter plot of the data, find the correlation coefficient, find the equation of the least squares regression line, use a regression line to predict a child's height at age 40 years. So there's a lot of stuff going on here. So let's do this scatter plot first. I'm going to actually write out the data. So let's do that first. So we got number 13. So in this case, age is our explanatory variable. So I'm going to say that's x is our explanatory. So that's 36, 38, 51, 54, 57, and 60. Y is our height, and that's our response variable. All right. So first off, we want to do a scatter plot. So all we're going to do is plot this data. I'm going to actually I'm going to actually do two of these. So let's do two of these because we're going to need two separate tables to calculate the stuff that we need to calculate. So I'm going to repeat this x, y, because we're going to continue. We're going to draw. We're going to continue this and extend it to more columns. Same thing here. So I want to rewrite the table twice, so I won't have to do it later on. All right. So now let's do the scatter plot, and then we'll use these tables in a little bit. So let's go ahead and let's do the scatter plot down here. All right. So for the scatter plot, all you got to do is you're going to set up an x and a y axis. If you look at the y values vary from 86 to 95. If you want, you can break the graph and start there. Let's go from 80 to 100, and we'll go by let's see, we'll go by I mean, we can go by 5s, but I don't want to go too high. So 80 to 100, we'll go by 2s. All right, so we got 80 to 100. Then we have so for the x, let's do 35 to 60. Yeah, let's do 35 to 60, but we'll go by 5s or something like that. You can go by whatever you choose. It doesn't really matter as long as your dots are pretty accurate. Okay, so so our first data is 36 and 86. So 36 and 36 is around here, and 86. 48 and 90. 51 and 91. 91 is between 90 and 92. 54 and 93. Between the 92 and the 94. 57 and 94. 60 and 95. All right, so it does seem kind of linear, right? It looks like it's a good linear trend. So it looks like the coefficient of correlation is going to be strong. R is going to be a good value here. So it looks pretty good so far. Let's label our values here. So this was age in months, and this is height in centimeters. Okay, so that's our scatter plot. Next thing, they want us to find the correlation coefficient R. So this is why we need the table. So the formula for the coefficient of correlation is R equals the sum of the z-scores for x and y multiplied together divided by n minus 1. Okay, so we got to find the z-scores here. So in order to find the z-scores, we need to find these guys. We need to find the average for the x's, the average for the y's. We need to find the standard deviation for the s's, the standard deviation for the y, the sample standard deviation. Okay, so that's what we need to do. So to find the average for the x's, you simply average out these x values. So if you did that, you would get 49.3, around there. If you average the y values, if you average the heights, you'll get about 91.5. If you did the standard deviation, so this you can do on the calculator at this point. So you could do this on the calculator, you would get 12.2. The standard deviations for the y on the calculator, 3.3. Okay, so now that we got that, we can calculate the zx, the zy, and the zx times zy. Okay, so if we want to do the first one, then for zx, the formula for z x is x minus x bar over sx. The formula for zy is y minus y bar over sy. So if we want to do the first one, then it would be x minus x bar is 49.3, over sx, which is 12.2. Okay, so that's how we would do that first one. And then sy would be 86, y minus y bar over sy. So that's how we calculate that. I'm going to erase that now and replace it with what it should be on the calculator, but that's how you would calculate the zx and the zy. Okay, so the zx, you got negative 1.91. For zy, you get negative 1.67. And then to calculate zx times zy, we multiply these two together. Multiply the two values, and you get 3.18. Okay? Now I'm going to give you the numbers for the rest of them now. So negative 0.11, 0.14, 0.39, 0.63, 0.88. For the zy's, negative 0.45, negative 0.15, 0.45, 0.76, 1.06. Now we multiply them. 0.05, negative 0.02, 0.18, 0.48, 0.93. All right, so now if you look at the formula, we have to do the sum of those numbers. So we have to add this. We have to do a total. of that last column. So if we add that last column, we get 4.79. So now we can go ahead and calculate it. 4.79 over n minus 1. Well, n is how many numbers we have. So how many x values do we have? So we have 6 values. So n is equal to 6. So we have 6 minus 1. And if you did that, you get about 0.958. Okay? So that is our R value. Next, so R is 0.958. So find the equation of the least squares regression line to predict height from age. All right, so if we want to figure out the equation of the least squares regression line, we're going to use this table over here to do that, by the way. Let me move this out to the side. Okay, so the equation of the regression line the equation of the regression line, remember, is going to be y hat equals a plus bx. All right, and the formula for b is the r value that we calculated times the sy that we calculated over the sx that we calculated. So we can actually calculate this because we already know what the r value is. So we said that the r value was 0.958. We know the sx and we know the sy. So we got the 0.958 r value times our sy. Our sy was 3.3. Our sx was 12.2. And if we did this, we get a b value of about 2.258. Now to do our formula for a is y bar minus b times x bar. And our y bar, we calculated that earlier. So that was 91.5. Our b is, we just calculated that here. And our x bar, we calculated that earlier as well. That was 49.3. And if we did that, we would get an a value, 78.78. Which means that if we plug those in, our equation for our regression line is 78.78 plus 0.258 times x. That's the equation of our regression line. All right, use a regression line to predict a child's height at age 40 years. So all you got to do is you got to do y hat is 78.78 plus 0.258 times 40, and that will give you what the height is. So y hat is equal to, this is for part D. So if you did that, you'd have to calculate that on, let's do that on the calculator real quick. You get 89.1 centimeters. All right, so that's how you do the regression for predicting at 40 years. Or this should not say years, this should say months. Sorry, that's a typo, not 40 years, 40 months. All right, now construct a residual plot. So if we want to do a residual plot, we'll need to calculate all the residuals. So we'll need to use this table right here. So remember, to calculate the residuals, all right, so to calculate the residuals, excuse me, we'll need to use the formula for residual, which is y minus y hat. So basically, let's do a column for residuals. So basically what we need to do is we need to plug in, or let's do our y hat first, sorry. Y hat and then y minus y hat. Okay, so again, to find y hat for 36, all you got to do is plug in 36 into our equation for y hat. So remember our equation for y hat was this. So to find y hat, you plug in 36 in for x there. I'm not going to show you that calculation. That's a lot. So it's going to be 78.78 plus 0.258 times 36. So we'll plug that into that x value. And then we'll repeat that for all of them. Okay. So if you plug in 36 into that equation, you're going to get 85.49. If you plug in 48 into that equation, now 91.16. Next one is 91.94, 92.71, 93.49, 94.26. So that's how you do that. The next thing is, now we want to do the y minus y bar. So this is where we subtract these two values. So 86 minus 85.49, that'll give you, or y minus y hat, sorry, it'll give you 0.51. Then subtract these two now, and I'll tell you what those numbers are. Negative 1.16, negative 0.94, 0.29, 0.51, and 0.74. So there's our residuals. So these are our residuals. So I'll say this is res for residuals. All right, so now that we got our residuals, we can actually plot them. Okay, so our residuals go here. Usually the 0 is in the middle, so you have your 0 for residuals, and then for the bottom, it's, in this case we're talking about age, so that'll be the same. All right, so now for our residuals, our biggest residual is 0.74. So it's between 1 and -1, basically. So very small. So between 1 and -1. So we could do that. So when the age is about 30, let's see here. When the age is about 36, hold on. Should this be 36 or 26? Let me double check the number real quick. Let me go back. Okay, it should be 36. Okay, so it's about 36. We'll say it's about 3.18. Or, sorry, negative 1.6. What was our number? 0.51. Okay, sorry. I was trying to go back to the table. So 0.51. When it's 48, it's about negative 1.16. So around here. When it's about 51, it's about negative 0.94. Let me go back to our number, to the table. Yeah, negative 0.94. Switch it around here. When it's 54, 0.29. Pretty small. 57 is 0.51. And then lastly, 60 is about 0.74. All right. So if you look at it, it looks like, you know, it's kind of hard to tell, but it looks like it's about, you know, what it should be. You know, some above, some below. There's like 4 above, 2 below. There's no specific trend here. It's kind of hard to tell if it's valid based off of this alone. Because we don't have enough data. But, you know, we'll just leave it at that. That's our residual plot. Interpret the validity from the residual plot. So, like we said, it's kind of hard to tell from this plot, but there are some up, some down. So, it's very hard to tell. So I wouldn't worry too much about that. Usually, I'll give you more data to do this, but we'll say that it seems like it should be fine. It's completely, it seems random, some up, some down. So we'll just say that. So it seems kind of random. So validity seems fine from the residual plot. Usually it'll be very obvious if there's a pattern, like you'll see five, you'll see all five of them go in a line or something like that. So usually it's kind of obvious. So it's kind of hard to tell from this. All right. So either way, if you said it's not valid and you give an interpretation, then I would take that as well. It's just very hard to tell from the graph. Okay. So calculate the standard deviation of residuals. So to calculate the standard deviation, we'll need to calculate, we'll need to give you the formula for S. So the formula for S, I'll just do it over here. So the standard deviation of residuals. All right, so the formula for that is S equals, we'll say S res for residuals, is equal to the square root of the sum of the residuals squared divided by n minus 2. Okay, so that's how we calculate the standard deviation of residuals. So basically, we have to add up so basically, this is the same thing right here as the SSR for the residuals over n minus 2. So that means the same thing. These two mean the same thing, okay? This means sum of the square of the residuals for y hat. That's what it means, sum of the squares. This is a sum, this is a square over n minus 2. So we'll need to find out the sum of the residuals, but we already found the residuals here, so we'll have to square the residuals. So that's what this column is for, so we'll have to square it. So we're going to square 0.51 to get the next number. Negative 1.16, we're going to square that, and so on. I'll tell you what those numbers are to save on time. So if you square those numbers, you get 0.26, 1.35, 0.88, 0.08, 0.26, 0.55. All right, now we sum those residuals. We do the total, basically. So the total for that, I'll do it in another color. It's going to be, let's see here, 3.39. Okay, so that's the total. I'll just box that to emphasize that. Okay, so that's our total. Now that goes here for the numerator. So we got square root of 3.39 over, we had how many numbers? We had 6 numbers, take away 2, and then we do the square root of that. Or I'm just going to do it all in the calculator. So if you did that, you get 0.92. All right, next you want to interpret this value. So if we want to interpret this, we would say that the typical or average distance from the predicted value, from the predicted height, is 0.92 centimeters. Okay. All right, so that basically the S tells you the spread and the residuals, like how spread out are the residuals. Basically, what's the typical distance from the prediction. 0.92, the typical distance, that's pretty small. So 0.92, that means the typical distance from our prediction is about 1 centimeter, less than 1 centimeter, which is pretty good. So now let's look at the next part. So we said this was about 0.92. All right, so calculate the coefficient of determination using the sum of the squared residuals. Interpret this value. All right. So coefficient of determination. So to do that, coefficient of determination. So the coefficient of determination is r squared. So to calculate r squared, you can simply, there's a couple ways to do it, right? You could do the correlation coefficient r and then square it, or you can use the sum of the squared formula. So sum of the squared for y bar minus sum of the squared for y hat over the sum of the squares of the residuals for y bar. So there's a couple ways to do it. Now, in the test, they may ask you to do one or the other. So I'm going to show you I'm going to show you how to do both, just so you can see and compare the results. So let's do the SSR first. Now we already calculated this, right? This we already calculated. That was this in red on the table. Okay, this guy. We'll need to calculate the y bar version of that. So in order to do that, we need to do another column for y minus y bar, and then another column for y minus y bar squared, okay? And that will give us that. So we already know what y bar is. Remember y bar, we calculated it earlier, and that was 91.5. So we'll need to do 86 minus 91.5. So that's how we calculate this first one, 86 minus 91.5. I'll just write it over here. And that'll be negative 5.5. So that'll go here, negative 5.5. And then we square that. So we do negative 5.5 squared. And that'll give us 30.25. And that'll give us that number. Okay, 30.25. I'm going to give you the rest of those numbers now. Next one will be 91.16 minus 91.5. So if we repeat that process, okay, we get about negative 1.5-ish. Let me double check this real quick. Okay, next one is negative 0.5, 1.5, 2.5, and 3.5. Okay, so those are our y minus y bar. We're going to square them real quick. So we'll get 2.25. We'll get 0.25, 2.25, 6.25, and 12.25. All right, those are our numbers. Now we're going to do the SSR for y bar. And that, in order to do that, we just got to add these guys. Okay, so if we add that, we get 53.5. All right, so those are our numbers. Now we're going to put them into the formula. So we have 53.5 for the top there and the bottom here, minus the SSR for y hat, which we said was 3.39. And then we calculate that, and then r squared is about 0.94-ish, okay? So there's our guy. Now, so now our r squared here is going to be, so this is our answer, but now we can double check it, right? So the r that we got earlier was 0.958, and if we square that, we get about the same result. Okay, so we get about 0.94. So if you compare those two values, they should be the same, or approximately so. All right, so that's how you calculate the r squared. So that's a pretty good value. Interpret this value. So interpret. So this means that we got a 94% reduction in the variability in going from the y bar to the y hat. Okay, so in going from in using the regression line. So basically 94% of the variability in the height can be accounted for by the regression line. So 94% of the variability in the height can be accounted for by the regression line. All right, that is it, folks. So I hope you learned something from this video. There's a lot going on, a lot of calculations, but I hope I was able to kind of expedite that, but also at the same time, you learned something and did a good review. All right, I'll see you guys in the next video.